Pluto is a distant and perplexing planet that was once fundamental to our nearby planetary systems family. However, disturbing announcements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a surprising revelation. They suggest that it is on a potential trajectory to collide with Neptune. But how could this happen, and what might be the consequences of such a massive event? Are we witnessing an impending crash? Or is there something else about this looming disaster? Join us as we explore the possibilities of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet partly due to its unusual orbit, remains a subject of interest and study in the scientific community. According to recent assessments by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising concerns about a possible disastrous impact between these two planets, which could pose a significant risk to Earth. How is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a staggering 248 years to complete a single orbit, meaning that since its discovery in 1930, it has not yet completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating drastically from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, tilted at 17 degrees to the ecliptic plane. This extreme deviation, compared to other planets, adds complexity to its orbital dynamics. Perhaps one of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For nearly 20 years in each orbit, Pluto is actually closer to the Sun than Neptune, challenging conventional expectations about their positions in the solar system. This raises a common question. Why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to understand its peculiar trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's stands out with its steep inclination and irregular shape. The mystery deepened with the realization that Pluto's orbit does, in fact, cross Neptune's. The complexity of Pluto's orbit highlights the intricate mechanics of space. The three-body problem in celestial mechanics involves predicting the movements of three objects, such as Pluto, Neptune, and the Sun, as they interact through gravity. It's like trying to determine their paths based on their initial positions and gravitational influences on one another. For Pluto, this issue explains how its orbit, Neptune's path, and the Sun's gravity work together in a complex manner. The terms alpha libration and degree libration, along with the VZK effect, are crucial to this discussion. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. Regarding Pluto and Neptune, this means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune, ensuring a spatial separation that prevents collisions. Degree libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an additional safeguard against potential impacts. Another significant factor in this situation is the VZK effect, named after three scientists, V. Zippel, L. Zay, and K. Kai, who studied how celestial bodies move in space. This effect describes how three massive objects, like Pluto, Neptune, and the Sun, exert gravitational influences on one another, affecting their orbits. In Pluto's case, the VZK effect helps explain why its orbit remains so unusual. Despite Pluto's orbit appearing chaotic, these stabilizing forces help keep it on a steady path. The VZK effect demonstrates that although space may seem unpredictable, certain patterns and laws maintain order. These factors ensure Pluto's orbit remains stable, preventing it from colliding with Neptune or deviating from its course. The three-body problem helps us understand how planetary orbits evolve based on gravitational influences. Studying this helps us learn more about Pluto, our solar system, and even distant stars and galaxies. Computer simulations in the late 1980s revealed that despite these stabilizing mechanisms, Pluto's orbit remains somewhat chaotic, with minor variations in initial conditions leading to massive differences over long periods. However, these remarkable properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos in check. Recent computational models have helped scientists understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a unique gravitational relationship with Pluto. Every time Pluto completes 2 orbits around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only factor. Jupiter's gravity also plays a crucial role in protecting Pluto's orbit, with Saturn contributing as well. These simulations show that Jupiter's gravity alone is strong enough to keep Pluto on a consistent trajectory for millions, even billions of years. It appears that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues moving safely through space without collisions. These gravitational interactions are fundamental to understanding the structure of the universe, as they maintain order and consistency in the movement of celestial bodies. Without these forces, the solar system would be a much more chaotic and unpredictable place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a domino effect on other celestial objects. Given recent discussions about Pluto potentially colliding with Neptune in the future, understanding its orbit is crucial. This knowledge provides a clearer picture of the dynamics of our solar system. Pluto's case demonstrates how even seemingly unstable orbits can achieve long-term stability through complex gravitational interactions and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos refers to the delicate dependence of a celestial body's trajectory on its initial conditions. In Pluto's case, even slight changes in its position or velocity can significantly alter its long-term path. In the vastness of our solar system, Pluto occupies a unique and intriguing position. While Pluto's orbit may seem erratic, the intricate balance of gravitational forces ensures that it remains in a stable yet highly unusual trajectory. This delicate equilibrium is a testament to the complex nature of celestial mechanics. However, despite its stability over long time scales, even minor disturbances, such as the gravitational pull of passing objects, the influence of distant stars, or the effects of interstellar matter, could potentially alter Pluto's orbit in unforeseen ways. One of the most critical aspects of Pluto's orbital behavior is its resonance with Neptune. This gravitational locking mechanism prevents the two bodies from ever coming too close. Essentially, for every 3 orbits Neptune completes around the Sun, Pluto completes 2. This synchronization ensures that their paths never result in a direct collision. This protective resonance is a well-documented phenomenon in celestial mechanics, providing stability despite apparent orbital intersections. However, could external forces disrupt this balance? Some astrophysicists speculate that over millions or billions of years, subtle gravitational perturbations from other planets, passing stars, or even dark matter interactions could shift Pluto's orbit enough to break this delicate resonance. If that were to happen, Pluto's path could become less predictable, increasing the likelihood of chaotic interactions with Neptune or other planetary bodies. Another critical factor is the long-term evolution of the solar system itself. Over immense timescales, the positions and gravitational influences of planets change due to complex interactions. Jupiter, the most massive planet in the solar system, has a particularly strong gravitational impact on everything around it. If Jupiter's orbit shifts slightly over millions of years, it could subtly alter Neptune's position, indirectly affecting Pluto's trajectory. In addition, recent studies in planetary dynamics suggest that the solar system might not be as stable as previously thought. Numerical simulations indicate that planetary orbits experience gradual variations due to the cumulative effects of small gravitational interactions. These changes, while slow, can have profound effects over billions of years, possibly leading to planetary realignments or even ejections. If Pluto's orbit were to be perturbed in this way, it might eventually cross Neptune's path in a way that could lead to a near collision or a gravitational slingshot effect, throwing it into a completely different orbit. But what would happen if Pluto and Neptune did collide? A direct impact between these two celestial bodies would be an unprecedented event in our solar system's history. Given their relative sizes, Neptune being 17 times the mass of Earth and Pluto being a mere fraction of that, the impact would not significantly affect Neptune. However, Pluto would be utterly destroyed, likely breaking into countless fragments. Some of these remnants could form a temporary ring system around Neptune, while others might be ejected into the outer solar system or even beyond. The potential consequences for Earth and the inner solar system would depend on the scale of the collision. If large fragments from the impact were sent hurtling inward, they could pose a risk to other planets, including Earth. However, given Pluto's distance and the gravitational influences of larger planets like Jupiter, the likelihood of direct consequences for Earth remains minimal. Ultimately, while the idea of a Pluto-Neptune collision is an intriguing theoretical possibility, current models suggest that the protective resonance between these two bodies makes such an event extremely unlikely. However, the continued study of Pluto's orbit, planetary dynamics, and long-term gravitational influences remains crucial for understanding not only our solar system, but also the complex interactions governing celestial bodies across the universe. As we look deeper into space and refine our understanding of planetary mechanics, Pluto serves as a powerful reminder of the delicate balance that keeps the solar system in harmony. Its orbit, once thought to be chaotic and unpredictable, is in fact a fascinating example of how gravitational forces work together to create stability amidst apparent disorder. Whether Pluto will remain in its current trajectory for billions of years or eventually face a dramatic orbital shift remains an open question, one that future generations of astronomers and astrophysicists will continue to explore. A position that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its structure and behavior. One of the most captivating aspects of Pluto is its surface, which is a complex tapestry of ice, rock, and various compounds. NASA's New Horizons mission, which flew by Pluto in July 2015, provided remarkable data about this distant world. The surface of Pluto is characterized by vast fields, towering mountains, and deep valleys. One of the most remarkable features is Sputnik Planitia, a giant heart-shaped plain made primarily of nitrogen ice. This area showcases a variety of landforms, including massive ice shelves and what appear to be flowing glaciers. The presence of these features suggests that Pluto may still be geologically active despite its great distance from the Sun and its low temperatures. Another fascinating aspect of Pluto is its atmosphere, primarily composed of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is thin, but shows interesting seasonal variations. As Pluto moves closer to the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior reflects the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply revolving around Charon. This unique relationship contributes to the complex gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small, icy bodies, is home to various other dwarf planets and potential impactors. This belt is a repository of ancient material from the early solar system, giving scientists a glimpse into its formation. Pluto's orbital characteristics may provide insights into the formation patterns of these distant objects, suggesting that interactions with larger planets may have played a critical role in shaping their current orbits. One of the key implications of understanding Pluto's orbital elements is the potential impact on how we understand the solar system's evolution. Gravitational interactions from neighboring giant planets like Jupiter and Neptune can alter the orbits of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to changes in orbits, potentially resulting in collisions or ejections from the solar system. As researchers continue to study the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to rename Pluto as a dwarf planet in 2006 was controversial, sparking debates about the nature of planets. In any case, Pluto's orbital relationship with Neptune and its position in the solar system serve as powerful reminders of the complexity of the universe. Through continued investigation, we can deepen our understanding of these distant worlds and the forces that govern their motion. As we continue to explore Pluto's unique orbital elements, it is essential to recognize how the gravitational forces exerted by distant planets shape the behavior of objects in the outer solar system. While Pluto's orbit may appear chaotic at first glance, it is precisely these intricate interactions that allow it to maintain stability despite its apparent instability. As we delve deeper into the mechanics of Pluto's orbit, we uncover more layers of complexity, shedding light on the dynamic processes that govern the motion of celestial bodies. One intriguing aspect of Pluto's relationship with Neptune is the long-term stability of their orbits despite their occasional proximity. This is due to a special resonance between the two bodies, known as a 3:2 orbital resonance. For every 3 orbits Pluto makes around the Sun, Neptune completes 2. This resonance keeps Pluto and Neptune in a stable configuration, preventing them from colliding despite their orbits crossing. The stability provided by this resonance is a rich example of how gravitational interactions can ensure the orderly movement of celestial objects. This 3:2 resonance is the result of the gravitational tug-of-war between Pluto and Neptune. Each time Pluto and Neptune approach each other in their orbits, their gravitational fields interact in a way that ensures their paths remain synchronized over long periods. The result is a system where, even as Pluto crosses into Neptune's orbit, the two bodies are always carefully spaced apart by the steady resonance. Thus, the likelihood of a collision is virtually non-existent.